Good afternoon. I'm Professor Sever. Today we're continuing Notebook 2 with Part 3, which will focus on linear equations and linear systems. And in this notebook, we will be working on row reduction. So let's begin. Let's look at this matrix. And now let's put the matrix in reduced echelon form, okay, through a series of elementary row operations. Let's begin. So what do we want to do? First, we want to notice that we don't have a 0 in the 1, 1 position, so we can do an interchange. I'll interchange rows 1 and 2. Okay, and we see the result here. Now, what do I want to do? Well, we know we want the leading entry to be a 1, and it's up to you whether you want to try to get the 1 first or get the zeros first. So what do we have to have? For echelon form, we need zeros below the leading entry. And for this example, I'm going to take that tack. So rather than scaling the first row to get a 1, which is perfectly fine, and I set it up so there would be no fractions if you did that, I'm going to show you that you don't have to do that. That's what a lot of people do, and there's nothing wrong with that. I'm going to use the 3 in the 1, 1 position to produce a 0 in the 2, 1 position. How can I do that? I'll use the type 3 elementary row operation, which is a linear combination. I'll multiply -1 times row 1 and add that to row 2. Again, I'm going to leave the arithmetic to the reader. You can pause the video at any of these stages and perform the arithmetic to see if you get the same result that I do. So applying that operation produces. So now, this was the last step. I'm just rewriting it here for convenience, since this is a kind of a scrolling effect here I have. That gives me a 0 in the 2, 1 position. Now, again, I've set this up. You could scale, but I don't want to do that just for illustration. I want a 0 in the 3, 2 position, the position that I'm indicating here. Again, so for illustration, I'm showing you how to get zeros without using the leading entry to be a 1. I'm not suggesting that that's preferable. I'm just doing it for instructive purposes. Okay, so if I want to do that, I'm going to multiply row 2 by -3/2 and add that to row 3. Again, pause the video, perform your own computation, and you would obtain the following. Again, so this is where we were. My goal is to get a 0 here. Let's see what we got. And I do. And I get more zeros as a bonus. And we see this is the matrix that's row equivalent to that last matrix by applying -3 times row 2 and adding the result to row 3. Of course, putting the result into row 3. Now, what do I want to do? This matrix is in echelon form. First thing to note. The goal is to put it in reduced echelon form. So what do I want to do? Where do we need the zeros? Above the pivot, that's in the 1, 2 position, and above this pivot, which would put zeros in columns 5 as I'm illustrating. It's arithmetically simpler to start at the back row, the rightmost pivot, and work leftward. So the forward phase of the echelon process works this way. You move down and to the right, clearing zeros below, as we did. For the reverse phase, i.e. when we're in echelon form, attempting to obtain reduced echelon form, you want to work from the right, moving up. Okay? Mathematically, it makes no difference, but arithmetically, it's easier because these entries are all 0. And as you do the computation yourself, you'll see what I mean. Let's look at an example. So to put a 0 in the 2, 5 position, I need to do -2 row 3 plus row 2. To put a 0 in the 1, 5 position using row 3, that's the key, then I'll do -6 row 3 plus row 1. So let me say this again. In the forward phase, as I said previously in this video series, you use the upper row to produce zeros in the lower rows. In the backward phase of the row reduction process, it is reverse to the forward phase. You use the lower rows to produce zeros in the upper rows. Why? Because you're clearing out, as we say. You're producing zeros above the pivots. So let's perform those two operations as I indicated, and let's see what we get. Again, this is just the matrix where we were. And again, applying those two operations, you've done the arithmetic, and you would have seen we have 2 zeros there. And notice this is the benefit or the beauty of having these zeros to the left of the pivot. Anything times 0 plus another number is itself. It never changes these entries. in this example, when using row 3 to produce zeros above it, the entries in this submatrix never change. I can just recopy them. I don't have to actually go through the arithmetic. Why? Because these entries are all 0. This is why it's faster arithmetically. So the only entries that are going to change are these, because these are the only entries that are above non-zero entries in the row that we're using to effect the change, which is row 3. Okay, what do we want? Well, now let's get the leading entry to be a 1 in row 2. How do we do that? Even though the reduced echelon form is unique, the sequence of operations that you employ to obtain it are not unique. We can all apply a different number of steps and a different sequence of steps to obtain the same reduced echelon form. So at this point, I'll multiply or scale row 2 by half. I could have done that at the last stage too, by the way. Let's see what we get. So I've scaled row 2 by a half. Here's the row. Now what do I want to do? I need a 0 above this 1, which means I need a 0 in the 1, 2 position. That's easy to do conceptually. Since this is a 1, we know it's 9 times row 2 plus row 1. Let's do the arithmetic and see what we get. As expected, I have my 0. Here's the original matrix. Here's the operation. This is what we were doing. So now I'm one step away. Is this matrix in reduced echelon form? No, because this leading entry is not a 1. So I'm one step away from achieving it. I will scale row 3 by 1/3. I could have done that on the previous step. The sequence of steps don't really matter. We each can do them in different orders, but this is the order that I've chosen for illustrative reasons. So let's scale the first row by 1/3, and we obtain the final matrix, and that's in reduced echelon form. And we've done it. Okay, we need to apply this process of obtaining first the echelon form and subsequently the reduced echelon form to solutions of linear systems. So this section's really important. Okay, so let's look at it. So remember, from Notebook 1, we discussed the nature of solutions to a linear system. There are only 3 possibilities. No solution, exactly one solution, which means a unique solution, or infinitely many solutions. Okay? So what we want to do is look at how do we describe those infinitely many solutions in that case, in such a case where there were infinitely many solutions. So let's see what we're doing. So we want to discuss the case of infinitely many solutions at this time. So the row reduction algorithm leads to an explicit description of the solution set when you have infinitely many solutions. So we need to see how does that work. So let's look at an example. So say I had an original matrix, which I'm not showing you, but suppose that I tell you through the process of row reduction, we obtain the following matrix. So first notice this matrix is in reduced echelon form. It's row equivalent to the original. So let's determine how can we write the solution. So remember, each row in a matrix corresponds to an equation of the corresponding linear system. Now, so here's what we would get down here. Now, this is not the original linear system. This is a linear system that's equivalent to the original. Why? They have the same solution set. Okay. So what we want to do is, and we'll see it written here, here's the process. Let's first identify what our pivot columns are. We have pivots in columns 1 and 2. Okay? And we know the system is consistent because there's no pivot position in the rightmost column. We know that there will be infinitely many solutions because we have a column that doesn't contain a pivot. We call that a free variable, or rather we would say the variable that's associated with that column will be a free variable. So if we have 3 columns on the coefficient side, we'll have 3 variables. We'll call them x1, x2, and x3. x1 and x2 are basic variables because there are pivots in those 2 columns. x3 is a free variable because there's no pivot in this column. So now what we want to do is really you want to solve, when you look at this system down here, you solve for the basic variables in terms of the free variables. So in this equation, I will solve for x1 in terms of x3. There's only one free variable in this case. I will solve the second equation for x2 in terms of x3. Doing so yields the following. Now, so x1 is 1 plus 5x3, x2 is 4 minus x3. Now, x3 is equal to x3, right? That's a triviality. Well, you could also say x1 is equal to x1, x2 is equal to x2, x3 is equal to x3. That's a platitude, or it's a tautology. But it's more meaningful to say, once we obtain the reduced echelon form, that I know what x1 is in terms of x3. See, x1's not free. If x3 were 0, what would x1 be? It would be 1 plus 5 times 0, which is 1. So it would be 1 plus 0, which is 1. If x3 were 0, I'm just picking a number for x3 randomly to illustrate the point. x2 would be 4, and then x3 would be 0. So what I'm saying is, see how x1 is a function of x3, x2 was a function of x3, x3, of course, is a function of itself and as an identity. But the point is, x1 and x2 are not free. If you know what x3 is, then x1 and x2 are forced. Okay, they're forced by these formulas here. Okay, so what we want to do now, let's recall, what is a solution to a linear system in 3 variables? A solution to a linear system in 3 variables is an ordered triple. Okay, so it's an ordered triple, and we need to write then our description for the infinitely many solutions as an ordered triple. So what we usually do, we pick a parameter for x3, we say let x3 equal to s, for example. We don't really want to use x3 itself. It's one of the variables of the original system, although you will see that. It's a little bit better to write it parametrically, so to find some other real number, s, to represent x3, then in place of the remaining x3s, you just put s. By doing so, we would see that x1 is 1 plus 5s. I have that here. Notice it's in the first coordinate of our triple. x2 would be 4 minus s. That's the second coordinate of my triple. And what is x3? It's just s. That's in the third coordinate of my triple. So this triple in this form, where the first coordinate is 1 plus 5s, the second coordinate is 4 minus s, and the third coordinate is s, is a solution to the linear system, which is easy to verify. You would plug it into these equations here and see that it works. And you would know that it's a solution to the original linear system due to the fact that this matrix was obtained by a sequence of elementary row operations. Therefore, the original system has the same solution set. And coming back to this description, what do we call it? Well, remember, for each value of s, you have a different ordered triple. So we call this the general solution to the linear system, because it's in terms of these parameters. In this case, there's only one, namely s. If you wanted a particular solution, then you could choose a value for s, such as 0, as I did verbally a moment ago. So if you chose s to be 0, then you would have 1, 4, 0 as a particular solution to the linear system. And again, since there are infinitely many choices for s, we can see there are infinitely many solutions to the linear system. And that concludes Part 3 of Notebook 2. In Part 4, we will formalize the theorems that I was just referring to about existence and uniqueness. I hope you enjoyed Part 3 of Notebook 2. Thank you. I'm Professor Sever. I look forward to seeing you in Part 4 of this series.